you already know what is the term atomic mass refers to, right? And in the case of isotopes, so say consider the carbon. Okay, carbon, it exists in three different isotopes: C12, C13 and C14. If you see the periodic table, okay, and you will see carbon in this way, and the name of the element will be written here. This is going to be the atomic number, and here you will see 12.001. okay, so that is the atomic mass. And sorry, 12.01, that is the atomic mass. Okay, here for anybody a common question will arise. Okay, so this is the atomic mass of C12 or C13 or C14. okay, because it have three isotopes, right? Okay, so that question it is being answered from this concept of average atomic mass. Okay, actually this is actually the average of atomic mass of the C12 and C12, C13 and C14 isotopes. Okay, let's see how the average atomic mass is calculating. See, consider C12 and C13 and C14. okay, we will see it's a relative abundance. Relative abundance is nothing but how much percentage of these elements, these particular isotopes are present on the earth. Okay, for example, C12 isotopes, okay, it is a 98.892, and C13 isotopes, it is 1.108, and that means it is in percentage. Okay, so the most common isotope of carbon, it is C12, so it is present around 98.892 percentage. C13 it is 1.108 percentage, and C14 it is 2 into 10 raised to minus 10 percentage. Okay, actually you might have already heard about the C14, right? Actually it is using for a carbon dating procedure, the determination of the age of fossils and all. Okay, and the atomic mass unit of these particular isotopes. So for example, in the case of C12, it is a 12, and for C13 it is a 13.00335, and for C14 it is a 14.00317. okay, let's see how we will calculate the average atomic mass. Okay, so then average atomic mass is it is 12 into, we will see this relative abundance. Okay, so it is a 98.892 divided by 100 plus 335 divided by into, okay, I will write here, into 1.108 divided by 100 plus, now we can write it is 14.00317, 2 into this is the relative abundance, right? Okay, 2 into 10 raised to minus 10 divided by 100. okay, so if you calculate, you will get a almost around 12.011 is going to be the atomic mass. Here you can directly write, okay, 0.98892 and 13.00335 into 0.0108, and here also you can write in the way. Okay, actually this is how the atomic mass it can be calculated. Actually if you see any elements which is having more than one isotope, so for example even oxygen, or the elements chlorine. Okay, if you see the atomic mass here, okay, so that, okay, here the element, okay, here the atomic number, and here the atomic mass, it will be there. Okay, this is always, it is going to be the average atomic mass. That means it is the average of all the isotopes provided it is multiplied by the relative abundance. Okay, so this is it about average atomic mass. Now about the molecular mass. See, molecular mass, like we know that every molecule it is composed of atoms, right? Okay, for example, it is H2O. It is composed of oxygen and hydrogen, right? Okay, so how we can calculate the molecular mass? It is a common thing. Even the school, 8th class children knows. Okay, so it is 2 hydrogen atoms are there. One is the atomic mass of hydrogen, and 1 into 16 is the molecular weight. Okay, almost 16 is the atomic mass of oxygen. Okay, so we can get it around 18 atomic mass unit. Okay, and if you are going to calculate the molecular mass of CH4. Okay, so molecular weight is equal to it is carbon, it is 1 into 12 plus 4 into hydrogen. It's a atomic mass is equal to 1, so it is going to be 16 atomic mass unit. Okay, or else you can take any molecule. For example, C6H12O6. Okay, so this is nothing but glucose. Okay, so the molecular weight is equal to 6 into 12 plus 12 into 12 into 1 plus 6 into 16. So we can get it 72 plus 12 plus 6 into 16. It will come around 96. Okay, and we will get the molecular weight is equal to 190 unified mass, or you can also write atomic mass unit. Okay, so this is how the molecular mass can be calculated. Okay, now there is again one specified term that is called a formula mass. Okay, so let's see, before going into this particular term, I will tell you in which situation we are going for this term. Okay, see, for example, sodium chloride. Okay, sodium, we all know that it is composed of Na plus and Cl minus ions. Okay, so even though we write its formula in this way, actually this molecule doesn't exist as a discrete molecule. We cannot just take a single or a single unit, N80. Okay, so for if we write it is Na plus and Cl minus, intermittently we can see Na plus again and Cl minus, again Cl minus, Na plus, Cl minus, Na plus, and so on. Okay, so it is it is actually this every ionic salt, it is like a sea of ions. Okay, so if you see Na plus, Cl minus, Na plus, Cl minus, so we cannot just like that, we cannot take a molecule, we cannot take a discrete or a single molecule. Okay, so Na plus, Cl minus, again Na plus, Cl minus. In this situation, what we will do, because we cannot take we cannot take in the same way we are taking carbon dioxide. Carbon dioxide, it exists as a single molecule, it exists as a discrete molecule. Okay, but in these kind of situations, it is like a sea of ions. It is just Na plus, Cl minus, Na plus, Cl minus. So it is spread like a sea of or pool of ions. Okay, so in those situations we will just see the formula. What is the formula of NaCl? It is NaCl, right? Okay, in that situation we will just to calculate its just to calculate the molecular mass, it's from its formula. Okay, so it is going to be 23 plus 35.5, so it is going to be 58.5. This is actually the formula mass unit. Okay, so the situations in which, you know, like when there is an ionic salt, not only NaCl, okay, you can also write a KCl or like potassium fluoride. Okay, in these situations and all, okay, we will go into the term that is called formula mass, okay, which is actually similar to the molecular mass. The concept is similar to the molecular mass, and in some specific situations we will be using this the word formula mass. Okay.